This video will move into section 2.8. We'll cover the topic of related rates, which is our last section in chapter 2. So we do have our test coming up after this. This will be the last unit that is in our second exam. Unfortunately, it's one of our tougher units. This is kind of like 2.7, a section where we start looking at some applications, some word problems, and we see the use of derivatives. And similar to 2.7, we could spend so much time. We could easily spend a month going through all different types of examples, seeing how and where we can apply these, getting little other bits of information to fill in so we know how to make the right equation in the first place. Because again, it's another big spot where we can talk about calculus is involved everywhere. Because now we get even further. Everywhere you get that expression, the rate of change, anything that has that sense. So the rate at which your computer connects to the internet, the rate at which you walk across the front of a classroom, the rate at which you walk to the bus stop, the rate at which you drink your coffee cup. Any of those things has some sense of rate of change. Something is changing over a period of time, and the rate at which that changes is the derivative. So, sounds easy, but actually can be, like I said, a little complicated. So we will get through a good bunch of examples. This is another section where, if you're using some of the extra resources, Dr. Bob, he has several videos that go with related rates. His first video, he introduces the topic, and then he has another, I think, 2 or 3 videos where he just goes through some common examples. Dr. Yee's notebook, he also has several good examples that if you want to try and have a nice worked out full solution to kind of check your work and to go along, maybe even just to get yourself started, not a bad problem to start with. Of course, we have our examples in our book. The math department, even before we switched to online, it was identified this was a tough topic. So I'm going to include some extra videos. One was made by me, but a few others made by other faculty to give you more examples. Because even though I say all of that, and experience is such a big part in all of calculus, in all of mathematics, in learning and understanding, but this is kind of a situation where practice certainly helps. And through this practice, you should be able to at least get on track. But again, it's still a tough problem. So if you still find yourself frustrated, again, I want you to realize this is a common spot. There are a lot of people that no matter how much time we spend on this section, it's still going to be a bit tough because there's lots to keep in mind. Okay, so after saying all that, what are we actually doing here? Well, related rates. 2 rates, or not, I shouldn't say 2, because we could have any number, but rates are related if their original quantities are related. That sounds like such a generic statement to start this off, but it really, really cuts right to the heart. Rates, and when I say rates, we're now starting to understand that we're talking about derivatives, are related. Related simply means that they're in the same equation. So that this first part simply points out that different rates, different derivatives will be in the same equation if the original quantities, if the original variables are also related, meaning in the same equation. So let me just already start off with a few equations we know. We know the area of a circle is pi r squared. This equation is relating the variables of area and radius. I mean, it's specific to the context of area of a circle, but it's relating these 2 variables, a and r. Don't be fooled, right? Pi is not a variable. I mean, actually, just a really fun, quick exercise. What's the derivative of pi to the 4th? If you said 4 pi cubed, you're not alone, but you're wrong. The answer is 0. Pi is just a number. It's not a variable. Remember that. That's like saying, what's the derivative of 2 to the 4th power? Well, 2 to the 4th power is 16. The derivative of 16 is 0. So again, just a very quick little note on the side, but just to come back over here, pi is not a variable. This equation just relates area and radius. Therefore, their derivatives will be in the same equation. And let me just show you how to do that right now. We're going to take derivatives. In this section, all derivatives will be with respect to time. So unlike the position, velocity, acceleration, they already had t as a variable inside the equation. Here we do not. Here we need Leibniz notation. But we're still taking derivatives. A is a variable, 1a, the derivative is 1, but you took a derivative of a with respect to t, so it gets marked dA dt. On the other side, pi is a number, again, just like if this was 4r squared, the derivative would be 8r, so pi r squared, the derivative would be 2 pi r. Still leaving that as a multiplier, kicking the exponent out in front, subtracting 1 from my new exponent, but I just took a derivative of r with respect to t, so that also needs to get marked dr dt. So now, this is still, we're really just getting started, everybody. But this is the connection. We knew this original relationship, this original equation that connected the original variables. By taking the derivative of that equation, we now get a new equation, and that equation has the derivative of area and the derivative of the radius. So it has those same derivatives, those same variables, their derivatives, their respective derivatives are now in a same equation. If the original variables are in the same equation, take the derivative, then those derivatives will now be in the same equation. But now let's just go off on the side for another moment, because now we're seeing this is really an application of implicit differentiation. So this was just a little bit of a trick question, just to see it and not be fooled by something like that. But if I said find d of dx of y cubed, well, that was our first example of implicit differentiation. We still did a plain regular derivative with the y, so y cubed has derivative 3y squared, but then it was marked dy over dx. And now we're doing that same thing with t, with time. If this was d of dt of y cubed, we get 3y squared dy dt. Okay? It doesn't have to be a different variable. If I had d over dt, and let's even throw a trig function in here, of cosine x, well, the derivative of cosine is negative sine, but the variable here is still x. You took the derivative of that variable with respect to t, so that would get marked dx dt. That's all I was doing up here. Taking the derivative with respect to t, I had to recognize, that's why I harped on pi for a moment, to be clear. These were the only variables, so that's where I was really focusing on my derivative, but they both need markings. Another common one that comes up in this section, you'd be surprised how often Pythagorean theorem comes up. How many different situations where you can draw a right triangle. One object is going this way, another object is going this way, and you want to talk about the distance in between those two objects. It's surprising how often that comes up. So this relates the sides, the lengths on the triangle, and maybe they represent something very specific in this problem. And we'll see examples like that. But if I took the derivative with respect to t here, well, all simple derivatives, these are separated by addition, that one's all isolated by itself, everything is to a nice power, so it's all nice and easy, 2a, but gets marked dA dt, plus 2b, but gets marked dB dt, equals 2c times dC dt. So this is notation, but technically it's also attached by multiplication. And that would be our derivative. So here's an original relationship, between multiple quantities. And that's why I want to point out it's not always two. This could be three quantities. Maybe one of these sides are fixed. Maybe B is a fixed side in this triangle, so its derivative would be 0. I mean, we'll get more practice here. We'll see these types of things. But just again, right now, just to get that practice, that this derivative, now this is what we get. And now sometimes we still have the original variables, but the point is that now there's a new equation and it contains derivatives of all the original variables. That's the direction we're going. So now I want to jump right in with a problem. And this first one, we keep talking about word problems and applications. This first one is really just implicit differentiation, but embracing t. So let's jump into a problem. We are given the equation x cubed minus 3xy squared equals 2y plus 4. And the question is, you're being asked to find dx dt at the point 2 comma negative 1 given dy over dt equals 3 units per second. Like I said, we are really jumping 2 feet right in, jumping right into a problem here. But it's all right here. You're given this equation. Well, you are being handed this original relation. Most of our word problems, we're not going to get that lucky. We're going to have to do something, see the problem, see what's being developed, see a right triangle situation. So you'll see that stuff in a moment. But we're being given the relationship. Here is some relationship that is connecting x and y. Okay? But now, when we, But now we are being asked to find dx dt. Well, if we have this original equation, how are we going to find dx dt? We're going to start by taking the derivative of that whole equation with respect to t. That's where the dx dt is going to come up. But unlike some of our implicit problems where we were just told, okay, find dy dx, and that was that, we're being given more information. We're not just finding dx dt generically, we're finding a specific value, given a specific xy pair, given a rate at which y is changing. And I kind of explained this a little bit in the implicit differentiation video. This is some curve. It's not a function, right? We can't solve it for y, but this would represent some curve. So let me just draw something on the side here. I don't even really care too much what it looks like. There's some curve. And what we have here, we want to know a rate at which x is changing at a specific y. So at 2 comma negative 1, well, let me actually fit this, so change my scale. 1, 2 comma negative 1. So let's kind of look at this point right here. At this point, if y is going up at 3 units per second, up because this is positive, well, for this point to stay on the curve, it can't just go up. It's got to go up, but while it's going up, it's got to follow the rest of this curve. So for this to go up 3 units, it had to move all the way over to here, which forced it to move left. It actually started a little right, but then it ended up going left at that same time. So that's kind of the idea here. And even more specifically, we're not going to plug this xy in right off the bat. That doesn't help at all. We are going to need the derivative before we plug these values in. And again, even though it's implicit, we've done that before. If I asked you to find, again, just off on the side here, quick little note, if I said find f prime of 2, you don't plug 2 into f. That never happens. You find f prime of x, then you plug in the 2. That's the same thing we're going to do here. So plugging the xy right off the bat does nothing. You want dx dt, take the derivative with respect to t. So look at my situation. 2 pieces here, product rule right here. 2 separate pieces here, nothing fancy. So taking my derivative, Starting off, 3x squared, but the x gets marked dx dt. Right here, product rule, I'm thinking of minus 3x is my u, y squared is my v, if you're using the full product rule notation. So u prime, I'll get negative 3 dx dt times v, plus the derivative of v, well, that'll be a 2y, and that'll get marked dy dt. So all that is the derivative of v times plain old u equals 2 dy dt plus 0. So again, really just doing an implicit derivative here. Just notice every variable is getting marked when I take the derivative, because every derivative is with respect to t. There are no t's in this problem. Every variable gets marked, but not everywhere. That's why I wanted to do a little product rule in this problem, just to get that reminder. I got a dx dt here because at that moment I was taking a derivative of x. There's not even an x here at the end, but it still has the dx dt. Similar at the end here. Okay, now you could algebraically solve for dx dt. These two pieces have dx dt. This does not. Move it to the other side. You could do similar things that we did with dy dx, but here's where we can take advantage. This is a given x, this is a given y, and that is what's going in for dy dt. So when I look at this equation, I want dx dt. I know it looks like ugly notation, but just treat it like that's your variable, and you've got values to plug in for all the other variables. So you can solve for dx dt generically. My experience is most people would rather plug in. Let's get 3, x is 2, so 3 times 2 squared times dx dt, minus 3y squared times dx dt. I mean, maybe you want to clean up your work a little bit here. That's your choice. I just kind of just threw the y squared up front here, but again, really doesn't matter. Just how they're connected, keep those relationships. I'm just literally plugging in. If you want to do some arithmetic while you plug in, of course, that's not a problem at all. So I'm going to continue. 2 times y times dy dt times minus 3 times x equals 2 times dy dt. Like I was saying a moment ago, with all this given information, after you plug this in, after you already first have your derivative, now you've got your moment and your other information. I know this derivative and want to find this one at this specific moment. Now we're ready to do that. Had the derivative, plugged everything in. Now I can solve, let's see, 4 times 3, I get 12 dx dt. That becomes plus 3 dx dt. So that'll be 15 dx dt. Over here, 2 times negative 1, so negative 2 times 3 is negative 6, times negative 3 is positive 18, times 2 is positive 36, equals 2 times 3 is 6. Subtract the 36, divide by 15. Units, well, again, this was a very generic problem. X and Y were just measured generically in units, and time here was second, so this is also in units per second. Not the easiest problem, and some people like this as a very generic problem to get them started, but believe it or not, some people do a little bit better once we start getting into the specific word problems. They feel like they have a little bit of a better sense as far as what is actually going on. So let's keep going. Nice first problem, but now let's look at a next one. For this next problem, just give me a moment, I need to write it out. We have some word problems here. So you're standing at a pond and you throw a rock into that pond, creating a growing ring of circles. If the radius of the pond is growing at 12 centimeters per second, at what rate is the area growing? The area of the circle growing when the radius is 20 centimeters. So it's kind of a big mouthful. And going back to, old traditional techniques with a word problem, if you're really trying to visualize something, drawing a picture can help. So thinking about this situation, again, we've got our pond. I throw my rock into the pond and I get the growing ring of circles, right? I get a small ring, then a bigger ring, then a bigger ring. That's that rippling, growing ring that we're talking about. And we notice that this picture, this is not a stationary picture. That again, it's not this is a bullseye that we're talking about. This was the first ring, then the second, then the third, then the fourth. This is a growing picture where at one point this was the radius, then this was the radius, then this was the radius. I'm just trying to make sure I don't overlap my radii. Just at every point, just trying to get from the middle to that far, far edge. And as we see, as the circle keeps getting bigger, the radius keeps getting bigger, and the area keeps getting bigger. Here's just a few little things. For me personally, I kind of like to get my picture drawn first, and then afterwards, I like to kind of fill in the extra information. Some people right off the bat can kind of fill in information. Some people can kind of set themselves up with letters here. In this problem, we're talking about area and radius. So the letters A and R already make a lot of sense here. But again, you could use different letters if you choose. So let me do this now. So as I go through it here, I read the problem. If the radius of the pond is growing at 12 centimeters per second, that needs to stand out. That information, that is given information. The radius is growing, so this would be a positive, that sense of grow, not decrease. But even the units, even if I didn't have that word growing, just the sense of the units, this is not telling me what the radius is, it's telling me the rate the radius is changing. So that will be the derivative of the radius, so dr with respect to time, so dr dt. Now, if I keep going here, the question itself, at what rate is the area of the circle growing? We know about the derivative of the radius. This question, at what rate is the area of the circle growing? They're in essence asking us, we know dr dt, can you find dA dt? Similar to this very first one, I gave you dy dt, you are being asked to find dx dt. The last thing is the moment. And again, like we said on the side, we don't plug x and y in right off the bat, we plug that in after, once we have the derivative established. That same thing happens here. We're not just finding the generic dA dt, we're finding that area specifically when the radius is 20 centimeters. Now, I wouldn't let the units bother you too much here. I'll make a point about that in just a moment. But just overall looking at this, that's the big picture. Have a little visual aid to help. Figured out what is being given and what is being asked. Well, if I want to know about these derivatives, I know about this one and I want to know about this one, well, I need to know an original equation. What is an equation that already connects the ideas of a circle, area, and radius? And that's the equation I gave you on the first page. We know that those original variables a and r are related in this formula. I will take the derivative of that formula. And again, it's literally the first one I started with. So that's why I did that a little quickly. The derivative of a of 1a is 1, and then it gets marked dAdt. The pi again is a multiplier, so the r squared is 2r. The pi comes along for the ride and gets marked dRdt. And now we fill in, right? We wanted dAdt, we knew dRdt, and we knew r. It doesn't help to plug r in here. You plug in r as 20 right off the bat, and you get the area is 400 pi square centimeters. That doesn't do anything in this problem. And for other people who try and break it down, they try and do this sense of proportion. Well, if the radius is going at 12 centimeters per second, how many seconds have passed before the radius gets to 20? But you don't know that's a constant. It's just in this moment how the radius is growing. So there's lots of things people try that put them in the wrong direction. This is what takes you in the right direction. Good visual, good notation and labeling, get that relationship, the derivative, and now we're ready to finish this up. This is what we want. Well, that means I'm going to need values for r and dRdt. They're both handed to us on a plate. di dt, 2 pi times 20 times 12. And what do we get here? That would be 480 pi. Units, well, I mean, this is where units, two things. Some people like to plug the units into the problem. It works, but I have to say I actually find that to be a bad habit. In a physics class, that's such a good thing to do. Make sure your units are, well, they match. You're not mixing like minutes and seconds and meters and centimeters. You know, you have to have like your common units. That's one thing. But secondly, units should confirm everything worked the way it should. But for us, we shouldn't be so focused. We need units here, but just think about the units. Area, well, if the radius is in centimeters, area would be in centimeters squared, square centimeters. Per time, well, time here was given in terms of seconds, so it's still in terms of seconds here. That's one way to go through and do it. But if you plugged it in, r had units centimeters, dRdt centimeters per second, centimeters times centimeters per second, that's not a coincidence you got centimeters squared per second. Centimeters times centimeters gives you that centimeters squared. So like I said, some people like to confirm that. I think it's actually more important to use the units to know how to plug things in. We're going to do a couple more examples, but just realize how I easily could have reversed this question. If I said, if the circle grows at 12 square centimeters per second, and then asked at what rate is the radius growing, I reversed the question. And that would have been seen by the units, 12 centimeters squared. Square centimeters don't go with radius, square centimeters go with area. So this square centimeters per second would go with the derivative of area. That would have set you up that this would have been plugged in over here, and you would have solved for dRdt over here. Okay, so that's just the first example. There's one in the book. They do one very similar. They've got a big spherical ball of ice that melts, and they use volume. Volume equals 4/3 pi r cubed. So, I mean, it's just a different formula that is very, very similar to this problem. Let's get into another problem. Let's say, so a whole new fresh problem. So our new problem. We have a leaky right circular cylinder, aka a soda can. Okay, we have a leaky right circular cylinder that is leaking at a rate of 4 cubic inches per minute. if the height of this can is 12 inches and the radius is 2 inches, at what rate does the height of the liquid fall or drop? So again, a leaky right circular cylinder, aka a soda can. So I'm going to draw a little picture over here, just like I drew my growing ring of circles here. So I'm going to start off with my soda can. I'll put a little hole in the bottom. So we've got leaking liquid. Well, assuming my soda can was full at the top, as it leaks, what happens? Well, the height of the liquid started here, but then it's down to here, then it's down to here, then it's down to here. As time passes and as soda leaks, that changes. Notice what doesn't change though. So this, I'll use H for height, but notice the radius in the can does not change. The radius of the can itself, and then even the liquid inside the can, well, liquid is very nice. As it leaks out, you're not going to have liquid up here and then no liquid down here. It's going to fall in this nice pattern. So R doesn't actually change. The radius is really unchanged in this problem. So now, got a little picture. Now I'm going back to the problem itself. I'm trying to identify my information again. And right off the bat, I see this leaking at this rate and looking at this rate. Well, first, it's a rate. It's a derivative. A derivative of what? Cubic inches. Cubic inches, just as we saw square centimeters or square meters, that's a unit for area. Cubic inches or cubic feet or cubic centimeters, that would be a measure of volume. So this will represent dV dt. And now here's two little things. You could realize that it's leaking and make that a -4 to encompass the fact that we're losing volume. Or this one will kind of work out naturally, that if we kind of ignore it here, that it'll come out as a positive answer, and we have to realize that's how the height is falling. But I'm sorry, let me not jump ahead though. So that's the first thing. We see that. That's derivative information, specifically the derivative of volume. Here's the height of the can. Okay. Here's my radius. At what rate does the height of the liquid fall? Rate of the height. We are being asked to find dH dt. We know dV dt. We want dH dt. We've got a little picture that'll help us, but now we have to figure out what is the association between V and H. And in this one, it can't just be limited to V and H. I'm looking at volume of a can like this, volume of a right circular cylinder, and our volume formula is pi r squared H. You might ask at this point, like, well, what, area volume formulas do I expect you to know? Not too many. The front cover in your book has pretty much any formula you might need. All right, that's what we were saying. As far as how far could we go? Well, we can go deeply into this class and learn more different types of equations that connect us to different areas of business, of science, of logistics, of healthcare, of all those different places. But we're going to stick with more basic problems here. So you'll see some basic area and volume, Pythagorean theorem, little bit with right triangle trig. That's kind of what you're going to see as your main source of examples. And that's also another good reason why you want to get plenty of practice, right? So we'll go through a couple more examples here. We're not done with this one, but we'll get a couple of examples past this one. and then the other videos that the math department has made, the one from me and a couple other people. And then again, some people still want to keep going outside of our textbook, Dr. Bob's videos, Dr. Yee's book. You do as much as you need. I certainly think the extra videos and the ones that we're doing here could be enough, but if you want some extras, to realize they're there for you. Okay, but now back to this problem. We're really just about ready to go down the home stretch, everybody. We're so close. The hard part in these is getting started. Getting some initial information identified, maybe a picture when it applies, but now we're ready to go. I've got the original. Oh, but here's the last catch, everybody. And this is what I was going to mention. It's so quick to just say, okay, I'm ready. I'm going to take the derivative. And especially from what we've seen earlier, the regular variables, that h is 12, that r is 2. We've seen things like that, and it's like, no, we don't plug that in until the very end of the problem. But before you take your derivative, one thing you should think about is, what are actual variables in this problem? Right now, it looks very quick and obvious, like, well, there's three, v, r, and h. There's three variables here. And that's what I was kind of mentioning in the Pythagorean theorem example I drew on the first page. It's like, well, there's A, there's B, there's C, there's three variables. But are they all actually changing variables in this picture? Volume is clearly changing. The volume is decreasing. We've already got the derivative. The height is falling as the volume, as the liquid leaks out, as the volume decreases. It makes sense the height will decrease as well. But does the radius ever change? It does not. So this is where, before we jump in and take the derivative, if you do this here, you're going to get product rule over here. And you're going to end up with a dr dt. And then completely separate from the problem, you'd be frustrated and think, what am I supposed to do with dr dt? I want dh dt, I know dv dt. What am I supposed to do with dr dt? And it would be up to you to realize that the radius never changes. The radius is a constant, so its derivative would be 0. dr dt would be 0 in this problem. But what's better than that? What's better is recognizing right off the bat, before I took the derivative, that r never changes. So specifically for this situation and what's changing, just v and h are my variables. I plugged in 2 for r here, and now I can take my derivative. And now this actually becomes an even easier problem than this one. dv dt equals 4 pi dh dt. That moment didn't even matter. It didn't matter if the height of the liquid was here or here or here. As the volume stays, as the change in volume stays at this rate, the change in height would be fixed as well. But still, just plugging in to finish. So I got -4 for dv dt equals 4 pi dh over dt. Divide the 4 pi over. I get -1 over pi. Units, well, if volume was cubic inches per minute, height would just be measured in plain old inches. So dh dt would be plain old inches per minute. -1 over pi inches per minute. Okay, so let's do one more. Like I said, the other videos that I definitely expect you to go through give you a few more little examples. There's one that deals with an area. I believe it's an area of a rectangle, as the professor sets up how you're playing around with your window format on your computer screen. That's definitely an example. There's another very generic example, just following a point that's moving along a curve. That's more similar to our very, very first example. I do a whole right triangle example, but let me do a right triangle example right here. We'll end this video with this last example problem. And let's set up a baseball problem. So, if you don't already know, a baseball diamond is a square. There's 90 feet between all bases. And again, I know my picture's not beautiful and it's called the diamond, but all of these are right angles. So I'm giving you this picture. And that's, again, if you go through the book, there is a baseball problem. And there are some where they give you a picture to try and help explain the scenario that they are setting up. So this is what we have. We have a runner on first base. Here he is. He starts running to second. At a rate of 10 feet per second. At what rate is his distance changing from home plate? So, well, how do we set this up? Oh, I'm sorry. I need to include one more little piece of information. Before I ask the at what, when he is, let's keep him 50 feet. When he's 50 feet away from first. And then, at what rate is his distance changing from home plate? So we have our picture. Here's our guy. Here's our runner on first base. He starts running to second base. As he's running along, when he is 50 feet away from first base, so from here to here is 50 feet, at what rate is his distance changing from home plate? Well, initially, here is his distance from home. Then here is his distance from home. Then here is his distance from home. As he's running to second base, I'm just drawing a straight line from home plate to the base runner, and that is my full visual. So even though you started off with this square, this is the right triangle we care about. That's the key to this picture. Because ultimately, I'm going to use this line. I'll use a capital L. Oh, I'm sorry. Here's the next thing. Unlike the previous problems, all of our letters, our variables made sense. We talked about volume, so V for volume, area, A for area, radius, R for radius. But now we're just looking at distances. So I'm going to use capital D as his distance from home plate. With that notation, this question is essentially asking, what is dd dt? But what else do I know? Right? Well, I come over here. Not only do I know this distance keeps changing. But now maybe I just want to use a letter for that. So I'm going to introduce A is the distance the runner is from first base. Well, now with that understanding, he's running to second at 10 feet per second. That is the rate that distance is changing. So we want dd dt with this notation. We know dA dt. So those are what we're trying to connect. And if we want an equation that contains these derivatives, well, what's an equation that contains those variables? There's my D. Over here is my A. And now, if we didn't see it before, now we need the right triangle. And one more time, it's easy to just say, well, A squared plus B squared equals C squared, or X squared plus Y squared equals Z squared, but apply it to your specific problem. In this specific problem, it would be 90 squared plus A squared equals D squared. Just like we saw in the previous problem. This side, this is a part of my right triangle, but I don't need another variable. If I called it side B and had B squared, I'd end up with a dB dt after I take the derivative. And once again, it would be up to me to realize that from my picture, dB dt is 0 because b was never changing. Look at my picture. This distance from home to first never changes. But the distance from the runner to first, well, first he's right on the base, then he's a little away, then he's further away. That distance is changing. The distance from home to the runner, well, first is this line, then this line, then this line. So A and D are legitimately changing in this problem. So we have to worry, either know their derivative or be what we're looking for. And in this one, nah, there's nothing for us to put here. So we'll just leave it just like the previous one. R was 2, so I plugged that in before I took my derivative. Here I realized this side was also 90 feet. I plug that in and then take my derivative. And I mentioned this earlier with pi. Don't be fooled here. Don't go 2 times 90 to the first power. That derivative is just 0. Here we get a 2a dA dt. Here we get a 2d dd dt. And we're just about ready to finish plugging everything in. And here is the last little tricky spot for related rates. And again, I mean, we've seen a lot. This is right at the beginning. I said this is a tough section. There is a lot just getting yourself started, getting yourself going. These problems can be difficult, but here is the last piece. People see this. We want a dd dt when A equals 50 feet. That was the moment we were talking about. But here's the problem, everybody. Look at what we know. We know dA dt, we know A, we want dd dt, but we need D. I don't want to say most. Many of our problems, that moment is just given to us. The very first problem, when the radius is 20 centimeters, there's your moment. Actually, that's the second problem. The first problem, when you pass the point 2, -1, that was your XY pair. That was your moment. Sometimes they might actually do it in terms of time. So I want to leave this problem like this, but I could have said, after 5 seconds, at what rate is his distance changing from home plate? And you would have to say, well, if he's moving at 10 feet per second and he's traveled for 5 seconds, you would have to compute and figure out that A is 50. That definitely comes up in a couple of problems here and there. So just to realize, the word problem itself, it contains a lot of information and it always contains enough. I'm never giving you any problems where we could say like, oh, not enough information. That never comes up. But sometimes we've got to work a little harder. And that's what we should realize right here. The previous ones, once we took our derivative and made any extra little considerations like we did here with B, we took our derivative, we were ready to plug in. But we should take a moment and say, do we have everything? And in this problem, we're missing D. So in here, we'd go back to the original. We already knew the one side was 90. But here, we know at the moment we care about, we know A is 50. And we could solve for capital D. Now, this is going to be a bit ugly here. So I get 90 squared is 8,100. 50 squared is 2,500. So we're getting 10,600 is D squared. It's not a clean answer, so I'm just going to leave it as the square root of 10,600. Not a problem. If you use your calculator, get a decimal, I'd have no issue with that. But again, instead of rounding here, I'll just leave it as an exact. Come back over here. Now I'm ready to plug in. Some of you might realize, hey, I could just cancel the 2's to make my life easy. And I would have 50 times dA dt equals D times dd dt. So 500 divided by the square root of 10,600 equals dd dt. For units, well, this is just basic distance. So A was changing at a rate of feet per second, so D also changes at a rate of feet per second. Okay, so again, definitely a little bit tough here. again, just how you plug in and compute a little bit, not too worried about that part. Just really trying to make sure we're getting the basic setup, seeing the notation, not forgetting our units. And here's the last thing, everybody. I recommended a moment ago, let's just kind of use good sense for our units. I'm not trying to trick you with that. So that's probably our best way. Sometimes the units might give us an indication what that quantity represents, whether it's volume or area, things of that nature. Plus or minuses, we saw that. We kept the minus in the previous problem, and we got a minus in our answer. So again, it made sense. That minus made sense that the height was falling at this rate. You could write that out, but that perfectly made sense there. So all the little extras still make sense if we think about them. We're getting all the things we should expect. But the last thing is, again, going back to the units. Units are a mess here. This would be measured in feet. This is feet per second. So right here, the 500 is technically in terms of square feet per second. But then this is measured in feet. So when you divide, again, you could track the units in the problem. Feet squared per second divided by feet would give me feet per second. But I still suggest it's much easier to just use the units and know what the units should be.